My name is Bob Gardner, and I will be your host today for our webinar on elevated temperature landfills, commonly referred to as ETLFs in the industry. I'm a senior vice president with SCS and oversee our solid waste practice. That includes engineering, consulting, construction, energy services, O&M services relative to landfills, transfer stations, MRFs, organic facilities, renewable natural gas, landfill gas to energy, and solid waste planning services. I was talking with an engineer for one of the major solid waste companies a couple of weeks back, and we were talking about elevated temperature landfills. And he had been involved with some of the initial investigations and remedial designs associated with the first elevated temperature landfills that we know about today. When everybody was really scrambling to deal with the heat and the liquids production, the gas quality changes, odors, material issues, litigation. He had hoped that we'd be seeing fewer of these as we go along, and he's been surprised by the elevated temperature landfill conditions that are showing up at more and more sites. Since those early days, we have learned much about what causes elevated temperatures in landfills and how to manage those conditions through research, engineering, and quite frankly, trial and error.
Yeah.
Today, our panelists include veterans in the landfill industry from the research, engineering, and field O&M and implementation perspectives. Let me take a second and introduce our panelists. We have Dr. Craig Benson, who is a distinguished professor emeritus from the University of Wisconsin-Madison, and also the Dean of Engineering Emeritus at the University of Virginia, which is my alma mater. So I'm excited about that. He has led research efforts sponsored by the Environmental Research and Education Foundation. His expertise really falls broadly in the disciplines referred to as geoenvironmental engineering. And it's the interface that really built natural environments and deals with issues relative to subsurface interactions between the waste, subsurface conditions, and so forth. He's often called upon by private and municipal landfill operators to assist in managing elevated temperature conditions. Bob Dick is a senior vice president with SCS, and he leads what we call our business unit 02, which is really the mid-Atlantic area operations stretching from Maine to South Carolina. He has 30 years experience in civil and environmental engineering related projects and solid waste. He has performed landfill gas and landfill engineering projects throughout the regions in some 15 states and foreign countries. He's a member of the American Academy of Environmental Engineers and Scientists. Robert Legaspi is a senior vice president as well, relative to our O&M services, Western Region Manager. He's a senior project manager with over 20 years experience in planning and directing and implementing landfill gas and groundwater operations, maintenance and monitoring and construction projects, really particularly related to landfill gas and the treatment processes associated with such. His work helps contain waste to prevent groundwater contamination, atmospheric pollution, and control the heat and water in landfills, and to capture that methane and reduce greenhouse gas. We're going to break this webinar into 3 parts. And first, Craig will provide an overview of elevated temperature landfills. He'll address the unique characteristics of elevated temperature landfills, including temperatures, landfill gas quality, leachate quality, and odors. Bob Dick will address the second part of our webinar, and we'll discuss the practical engineering issues associated with elevated temperature landfills and some example strategies that we have deployed managing these kinds of very difficult facilities. And not least, but Robert Legaspi will round out the third part of our webinar by discussing really the practical operational and maintenance issues associated with elevated temperature landfills, really where the rubber meets the road in terms of having, when you go out to a site and you have geysers that are blowing out wells and so forth. Robert has to deal with those, and so I think you'll find that very interesting. As Diane mentioned, if you have questions or comments, the QA button on the bottom of your screen, you can post at any time. I'll be kind of keeping track of those as we go along, and as appropriate, try to bring those into the conversation. So let's turn this over to Craig. And Craig, if you could really kind of set the stage for the better understanding of elevated temperature landfills.
Great, be glad to do so, Bob. I started working on elevated temperature landfills about 15 years ago. It was countywide landfill, and it was a condition that had just had everybody by surprise with very high temperatures, very strong odors, a lot of settlement. And it seemed to be a one-off at the time. That site got resolved, and there was some thinking at the time that it was fairly unique. And then a couple years later, I got involved in another elevated temperature landfill at the Congress landfill in Chicago that was hot for very different reasons, but had many of the same symptoms. And then at that point, we thought, well, maybe these were a couple of one-offs. And then Bridgeton landfill came along. I got involved in that a few years later. And we realized at that point that this was a phenomenon that was in the industry that we were going to have to deal with. And at the time, there was even some discussion, is this an existential threat to the industry? Well, perhaps that was perhaps too much of a statement. But what we have learned since then, at that time, people were pretty worried about how these were behaving, how we should manage it. But through thoughtful study, practice, I think Bob said very nicely, trial and error, we figured out how to manage these sites. Why do they form? Why do they get started? How can we prevent them if we can? If we do have an ETLF, what should we do about it? And what are the telltale signs of an ETLF that might be occurring in the future? Some of the characteristics that we see at ETLFs is wellhead temperatures that are persistently above 55 degrees C or 131 Fahrenheit. So it's essentially our threshold for an HOV, but not just one well. Wells over a substantial area of a cell or cells. So not one isolated hot well, but a collection of wells over an area where there's persistently above 55 degrees C. Other things that we see, primary gas ratio will tend to be declining. Methane will be dropping, the CO2 fraction will be increasing. That corresponds to elevated temperatures, affecting the methogenic bacteria and their ability to create methane. Another thing that we'll see is carbon monoxide and hydrogen in the landfill gas. First, historically, when we saw carbon monoxide in the landfill gas, we said, uh-oh, we have a fire, we need to turn the gas system off. Well, we learned that carbon monoxide is actually a decomposition byproduct of organic substrates like MSW at elevated temperatures. And that's very well documented in literature. And we'll see hydrogen along with it because we'll have suppressed the methogenic bacteria and their ability to process hydrogen. So we'll see both of those. We'll typically have very low or no oxygen. So these are clearly anaerobic conditions. Other things that we see outside of gas, increased leachate production, often very large leachate volumes that we have to deal with. We'll see why that is in a bit. High strength leachate, high BOD, high COD often will climb. And we'll also see elevated VOCs in the leachate. These are all the byproducts of exposing MSW, organic substrates, to high temperatures in the presence of water. And the other part that we'll see is substantial settlement. We'll see many of these, but not necessarily all of these at any given ETLF, but they are indicators. What they aren't, and I think this is important, these are not landfills that are on fire. These are not landfills where we have smoldering combustion. There's no combustion or oxidation reaction occurring. These don't have any oxygen to support a reaction. They're also just not landfills where we have an isolated hot well. In fact, I did a survey, a national survey, and about 30% of the MSW landfills in the United States have at least one hot well. So hot wells are fairly common. It's really when we've got a collection of wells that are persistently above 55 degrees C and 131. I want to emphasize at the end that most sites, if they have elevated temperatures that are isolated, don't have problems. ETLFs, while they are not fun to deal with, are a relatively uncommon occurrence relative to the number of landfills that we actually have in our portfolio in North America. Things that we see in landfill gas, I talked about earlier on that previous slide, but this is shown graphically. You can see carbon dioxide concentrations increasing, methane concentrations diminishing due to suppression of methogenic microbial communities. What's important, if you look at that in terms of the ratio of methane to carbon dioxide, you can see typical healthy MSW out here with a ratio above 1, and it's just sliding over time, diminishing And at the same time, the temperatures are increasing as well at this particular site. One of the things that we don't do enough of in our industry is graph up our data. We often will report data, lots of tables, lots of reports going into agencies, but we're not looking at the trends. And one of the things that we've learned clearly is watching for trends, examining the data, looking for those telltale signs are the things that we want to do. And one of those is primary gas ratio, methane to carbon dioxide ratio. If it's showing a trend like this, that's an alarm bell. We got a problem. Let's look into it. Other things that we'll see, I mentioned BOD and COD. We have a healthy landfill that's well decomposed. Our BOD to COD ratio may be as low as 1 in 10. That'd be for a healthy, well decomposed waste. That same waste, if it gets warm, if it gets hot, the BOD to COD ratio will climb, largely because we're decomposing organic matter that's in the waste and liberating it into the leachate. That will have higher BOD, will have higher COD as well, both will go up. And the ratio of those two will become closer to equality over time. So BOD to COD is a good indication as well, watching that temporally over time. We often see as well in many ETLFs often occur in wet sites. We'll talk about why that is in a bit. And if we're looking at dual phase extraction in wet sites where we're pumping out gas wells, we have a liquid pump into the gas well, examine that data. Look at the leachate chemistry in the gas well. If it's climbing in terms of BOD to COD ratio, that's a problem. Another thing we'll see too is the pH will tend to drop from healthy conditions of high 7 to around 8 to 5 to 6, largely because we suppress that methogenic bacteria that consume our hydrogen in our solution. I mentioned organics. This is another one of the telltale signs, and you'll typically see this best if you're pumping dual phase gas wells and looking at that leachate. But what we'll see is organic concentrations will typically be about 10 times what we would normally see in leachate. Things like phenols. Acetone is one that's very, very common. MEK, benzene will be 10 times higher. Why is that happening? All of these constituents are within our waste. They're being liberated as that waste is essentially being decomposing under elevated temperatures. And some of these compounds are all just decomposition reactions. That organic substrate is being degraded in our landfill like a reactor. It's like almost like an oil and gas refinery, but we're doing it with our organic substrate. And in fact, if you look at folks who work on biomass decomposition and MSW decomposition in the chemical engineering literature, they actually see this as an attribute. But this is one of the things we want to keep an eye on. Are we seeing these high organic concentrations? They're very common. And one of the telltale signs I always look for, do I see this in my leachate? Other things that we see, and I don't want to scare you with these, but it may scare you a little bit. One of the things that we see is carbonation carbonaceous organic materials. And this makes people think often, oh, I've got a fire because I see something that looks like it's charred, right? Like this ones I show over here on the left. That type of charring occurs under anaerobic conditions with elevated temperatures due to a process called endothermic pyrolysis. We've shown this very clearly in the laboratory and in the field that these type of conditions with charring, which look like they've been burning, in fact, are not burning at all. They're just a carbonation or carbonation formation in the landfill. Leachate with high pressure and temperature. You don't want to see a landfill geyser like this, but I think you'll see a little bit later on. They do happen. They are common. Because we have high temperatures, we have often have perched layers or confining layers within our waste mass that allow pressures to build up. We will get superheated, pressurized leachate at depth. Sometimes we'll have leachate that's at temperatures on the order of 300 degrees Fahrenheit and still liquid. And you might say, how's that possible? It boils at 212. That's because it's under pressure. One of the things we'll see is high pressure conditions. This is something we really need to be careful about. Robert will talk about a little bit later. And the other thing is we see lots of settlement, lots of leachate. And I think there's some wonderful experiments that Nicole Burge at University of South Carolina did with organic material, where she took just an organic substrate that might be in our waste, heated it up under an anaerobic, oxygen-free environment, took this specimen right here, just put it up to ETLF conditions. And this is what she got from that organic material. The water was liberated, the solids essentially fell apart. Why do we get lots of settlement? That's why. Why do we get lots of leachate? That's why. We soften up the materials, liberate the water that's in the pores, and that also becomes a very soft, compressible material. I want to emphasize before I leave this slide, not a fire, not combustion. None of this is caused by fires. You might ask, why do we get leachate that's so strong and odoriferous? You know, what's actually going on? If you have a crock pot, if you do this over the holidays, you're seeing this all the time. You put all your nice organic material in the crock pot, you put some water in there, that's leachate in our landfill. We put the lid on, we turn the heat up, and we let it sit. This stuff softens up. The materials within the solids decompose, break down into our leachate. We get, of course, in our crock pot, we get a nice aroma. We don't get quite as nice aroma in the field, in a landfill, but it's the same phenomena. It's just that breaking down of organic materials under elevated temperatures, under anaerobic conditions, just like we'd have on our kitchen counter, very similar conditions. It's an endothermic pyrolysis reaction. Now, those are all the things that we see. Why do they happen? Why does this happen in landfills? What's going on? In our conventional landfill, like I showed here with my simplified schematic, we've got heat that's being generated from microbial communities, and we're pulling that heat out regularly. We're pulling it out through leachate, we're pulling it out through gas, it's radiating into the subsurface, it's also radiating into the atmosphere, and it's being convected away by wind. And in a healthy landfill, we're in a balance. That is in a thermal balance between the heat losses and the heat that's generated by our microbial community. Let's put in a waste form that generates some heat, and then things get out of balance. Then we can't, because it was in equilibrium before this in our natural condition, we add some heat, we don't have an ability to radiate it away. And as a result, the temperatures build up. I believe in most ETLFs, they've built up for years before we ever see them. And then we have to deal with the ramifications of that. What may cause those? We spent years looking for the smoking gun. We didn't find the smoking gun. I think there's lots of smoking guns out there, but waste forms that we bring in that are special waste commonly, oxide hydration reactions are one potential cause. They tend to be pretty quick, so they may not be the most significant factor. Carbonation reactions, for example, with coal ash, these are long-term slow release reactions, but very exothermic. And then corrosion reactions as well from different types of metals and the like, where they're very strongly exothermic and potentially fairly slow reactions. So we're building up that heat over time. One of the things that we've learned is look at our special waste carefully before we accept them and think about how to dispose of them without causing a problem in our facility. You might ask, if I do have this problem, am I going to be able to solve it quickly? We can treat the symptoms relatively quickly. And I think we've had really good experience at the Bobs here and I recently treating the symptoms, but the high temperature conditions go on for a very long time. This is actually a site I've dealt with in the Midwest, and it's taken 10 years for those high temperature conditions to cool back down to normal and to become a new equilibrium state. So it will take a long time to get back to normal. So what are the things that we found to be really critical actions? And we'll hear more about these from others. Remove the heat. Get the heat out of the landfill. That's what's causing the problems. Dual phase extraction wells at wet sites are one of the best ways to do that because leachate has a lot of heat in it. We pull the leachate out, we're pulling the heat out. Extract gas vigorously. ETLFs has strong odors. We want to extract the gas that's going to alleviate offsite odor problems while also removing heat. And we all know offsite odor problems cause us lots of other problems as well. And then cap the surface with a geomembrane. Installing a geomembrane to cut surface emissions while we're managing and removing the heat to minimize odor emissions as well. And we found that the EVOH geomembranes really work well in that regard because they have very low gas transmission rates. And so that's a kind of a quick whirlwind tour of what I've learned in the last 15 years in this topic. I think we'll pass over to back to Bob.
Yeah, thanks, Craig. A couple of questions came in. One of questions was, how is it possible to have 40 to 50% hydrogen when no aluminum waste is present? And acetogenesis typically only yields up to 20% H2 hydrogen. That's question number one.
That's a tough one. We get it right out of the gate that are hard. Well, one of the things that we need, every site is unique. And some sites will have different reactions that can create hydrogen. So for example, just in some of our decomposition reactions, we will get hydrogen as a byproduct of that. We will suppress methogenic bacteria, which will essentially suppress our ability to process the hydrogen that we normally create from our decomposition reactions. And we may have some of the waste forms that are generating heat, producing hydrogen. So it's always a potpourri. And I think it's always a little hard to point at which one is causative. Really, it's treating the symptoms that we find to be most important.
Another question that came in was with respect to exothermic reactions. The slide mentions auto-Schroeder fluff. Can you provide some explanation as why that's the case?
Well, there are concerns about auto-Schroeder fluff because it contains metal particulate in it, both iron and aluminum. The fine aluminum is highly reactive and highly exothermic under landfill conditions, can be. I think that the jury is still out about the significance of the heat generating capacity of auto-Schroeder fluff, but what we have learned is for any special waste stream that we're bringing in, we need to think very clearly about what is its potential to generate heat under landfill relevant conditions. That means under conditions where it's going to be under stress, when it's going to be anaerobic, and where we'll be surrounded in an environment that's predominantly carbon dioxide and methane in the gas phase, and running tests to evaluate that.
Hi, gentlemen. I had a question come in on my phone. If temperature at wells have been running pretty steadily and consistent, although even not at the same temperature in a landfill for considerable time period, is there a certain amount degree increase that should trigger an evaluation or investigation, or a certain percentage increase of the steady temperature for that particular well or probe?
That might be a good question for Robert, since he's in operations.
Sure. Yeah, if you're seeing that type of temperature and it's a steady temperature, what you'd want to do is look at and test the well for CO and for hydrogen. So that would give you the answer or give you indications if you are actually seeing an ETLF occurring in that around that well. So you would be looking for the hydrogen in the percent. Around 2 to 3% is iffy. If it's over 5%, correct me if I'm wrong, Bob or Craig, but then you would have a positive indication that you may have the beginnings of an ETLF occurrence in that area.
Only thing I would add is just always look at trends, right? If you have concerns, graph the data over time. If things are changing, then typically something's going on that needs attention. It may be an ETLF, it may be something else.
Thank you, Craig. And Bob, from your experience, really, what are the consequences of elevated temperature landfill conditions on things like landfill gas system designs, the materials that we use in the construction of well fields, for example, drilling techniques, obviously some unique things when you're going deep and hot, and other construction issues that we face? I know it's a fairly broad question, but let's break it down first from the landfill gas well field perspective, and then maybe look at blower and flare stations and other parts of the gas system that might be impacted.
Thanks, Bob. Yeah, in the early days of the landfill gas industry, common rule of thumb for spacing of wells might be 1 well per acre. And what we see on these ETLFs is that you just have to throw that type of legacy rule of thumb out the window. On some of the ETLFs I've worked on, we've put wells, closer than 100 feet on center, And those wells are also being drilled much deeper for years in the industry. In kind of a standard anaerobic digestion landfill that's behaving properly. We didn't have a whole lot of incentive to go much below 100 to 120 feet. And, as we got into the ETLFs, and that circumstance seemed to be being demonstrated and exhibited at much more landfills, we certainly encouraged our gas construction and drillers to go much deeper. And then, there was notoriously some wet sites in the wetter parts of the country, maybe the Northeast, Northwest, Southeast, but the liquids dewatering is definitely an absolute imperative to be in conjunction with each and every well that's going into an ETLF. It necessitates that dedicated dewatering pump or some other means of passive liquid evacuation, because these wells tend to get watered in, and that impedes gas collection. Your objective is to remove liquids because of the density of the leachate within the waste mass. You can accomplish a lot of thermodynamic benefit by heat transfer by extracting those liquids. And then we do things like, look away from our traditional PVC and HDPE well casing pipes and consider steel piping, stainless steel. We have to introduce high temperature pipe materials, hose materials. Everything is hot. The pump's hotter, the interior of the well's hotter, the well head and the valve and the flexible hose, and even into the actual piping itself is subjected to much more heat. So you got to do things like forbid any weak fittings. And then there's certainly all of the drama affiliated with trying to drill in what is a low shear strength material. The waste, we've all drilled in regular landfills for years and said, oh, it's kind of mushy down there, or the waste doesn't have much structure or resemblance to the way it went in. It's well decomposed, but ETLFs are especially notorious for just having a really mushy goo type thing. And so it's hard to advance the bucket auger through that. So you have to think of things like drilling polymer, which is not favorable to put that stuff in there because it can plague or afflict your well. On the other hand, it may be the only mechanism by which you'll get to advance your well into the really wet stuff. So those are some things in the well field. If I switch over and start talking about the design circumstances at the gas mover system and the combustion units, what I call the control apparatus for landfill gas, you've got kind of a dual circumstance afflicting you. Number one, your gas quantity goes up. So just remember your ideal gas law, PV equals nRT. As the T side of the equation increases dramatically, the volume of gas is going to increase. So you just have more of the stuff, gas. And as if insult wasn't enough to injury, now it's got pretty, substantially degraded BTU content. So it's more difficult to maintain combustion. So you have to consider potentially things like perhaps a thermal oxidizer for this reaction gas. It doesn't have near the BTU content of good old fashioned landfill gas because it's being formulated in an abiotic environment. And so you have a decrease in that. You have to think about your flame arrestor and perhaps even introduce supplemental fuel to maintain combustion. Bottom line is a lot of these ETLF sites, typically, as Craig pointed out, they're oftentimes large, deep, and wet landfills. So there's usually some portion of the waste matrix that is behaving normally under methanogenesis and can be preserved for your landfill gas to energy project as you attempt to resuscitate the bad acting portion of the waste that's misbehaving in an ETLF and is necessitates the reaction gas to be segregated. Yeah, I know you were going to ask me about the common strategies for heat removal and the techniques. Craig hit on this a little bit about really what we've seen as far as a pragmatic and practical strategy for heat removal is through fluid extraction, both the liquid and the gas. And what you're trying to accomplish is some impediment to the propagation of the reaction into those portions of the waste that are unaffected at that moment in time. And then also, as Craig pointed out, over a long period of time, you can actually cool the reaction zone, the hot zone, and restore it to proper methanogenesis. I have heard of others. I've never been involved in a project that really attempted to implement a radiator system or some sort of heat exchanger. We've talked about in the industry the idea of geothermal and that type of an idea where you can introduce some sort of liquid to waste matrix heat transfer and try to get that to work. I think that's something that's been interesting and theoretical, but from a pragmatic standpoint, what we know does accomplish the mission here is removal of heat through extracting hot gas and hot liquids.
So in terms of the impacts of heat accumulation, what is your sense of some of that and how you manage some of those impacts?
Yeah, you certainly have this issue of diminished methanogenesis, and I talked about that. You definitely have the personnel safety concerns. One of my sites, we debated about putting some steel probes, temperature probes. We weren't even pulling gas or liquid out from that, but just the top of the above ground portion of the stainless steel probe casing for temperature monitoring. Someone hit it with the IR gun and said, "Oh, heck, that thing's 205 degrees. Don't let anybody walk up and touch it." And so, a lot of times from an engineering standpoint, we aren't used to protecting some of the above grade portions of the assets from just being visited by technicians who might lean against something, in addition to all the other potential exposure issues to the gases and leachate that we're trying to extract out there. Certainly the high temps melt stuff, so hot gas, hot liquids melts and deteriorates materials that we're relying on their engineering properties to actually perform their function. Another issue is just the regulatory aspect. Meanwhile, kind of in the background, as you're managing this misbehaving landfill and trying to institute best management practices, all the sites I've been on, the landfill owner has kind of this annoying chatter from the regulatory agencies who remind them of NSPS and NESHAP provisions in terms of temperatures. And then you definitely have, Craig mentioned, the superheated liquid, the high pressure geysers. And so the just quantity of liquid that's showing up in sumps, and it brings a lot of the debris. You're almost shredding it, or he mentioned liberating the liquid, and so you have this kind of very soft solid matrix structure that tends to flow into sumps. So you see a lot more solid debris, so things get fouled up. You're aggregate. And then, of course, when you are successful in getting liquid and gas, it just comes with a lot of the stuff that was in the waste. And one of those is the biological foam. So I think on the next slide, we have biological foam at non-ETLF sites, but at ETLF sites, as Craig mentioned, the BOD, the COD, and the leachate is extremely high. You start agitating that stuff with any type of action discharge. And, you know, from a operations and engineering standpoint, we see foam in a lot of places, but it's specifically problematic at, you know, ETLFs. And so there are management techniques, and one of those is a lot of anti-foaming materials being sprayed into to try to keep that down, Bob.
Yeah, I think, you know, one of the questions that was asked was with the lowering quality of the gas that you have, you know, one of the questions is how do you manage the CO and the H2O odors, you know, the odors that come out of the gas and the emissions and the operation of the gas, the flare system, for example. You have a flare or engine generators. What are the strategies for dealing with that?
Yeah, some of the odor techniques were, you know, much more aggressive about recommending things like wellbore skirts at pipe penetrations at ETLFs and foam seals around the soil pipe interface. Odors get out in terms of you know, gaskets and connections. We use cam lock fittings instead of just a hose clamp. We kind of you know, prohibit any type of hose clamp things and always look for hard fittings, whether that be bolted flanges or cam lock fittings for connections. Things like in the leachate, you know, you might have had some sort of open top tank when these frac tanks come in. Most ETLFs are kind of in a war zone, a crisis mode, and a lot of the sites that I've worked on are managing liquids because there's so much of it, it exceeds the capacity in their normal surface impoundments or their covered storage tanks. So there tends to be a lot of frac tanks around, and, you know, thinking about ways to cover those. And so from an odor mitigation, odor abatement standpoint, the small things that plague you in terms of contributing to offsite malodorous conditions, you're trying to identify those and proactively address them with some of these techniques I mentioned.
Craig, I know this is a subject that's close to your heart, and Bob, I know on one of the sites that we're dealing with, we're having this problem with what is called black goo. And a nice technical term, but it's something that we're having to deal with. And just curious, both Robert, Bob, or Craig, your 2 cents on that subject. Craig, you're on mute, by the way. Just curious about your experience in dealing with those kinds of materials. What are we seeing? What is this stuff?
Yeah. Well, I can talk a little bit about what it is, and it is ubiquitous and pervasive. We see it at ETLS, but we see it at other sites too. And we've been studying this pretty intensely for the last 18 months. And largely what we found that most of the black goos, not all of them, but they are polyacrylates. They're a hydrophilic polymer, a polymer that likes to bind water molecules that are in our waste stream. And they migrate, they tend to get dissolved into our leachate, and then they accumulate in leachate collection systems, and they accumulate in dual phase extraction well risers, and where they tend to get sticky and plug up pores, they plug up pumps that get stuck on everything. And these polyacrylates are things that are in everyday life. If you have young children, you're using them all the time for wastewater control. If you're making your barbecue grill and you've got a steak and it comes from your butcher and it's on a pad that absorbs the liquid, that's also got polyacrylate in there. It's just a very common hydrophilic polymer that's in our waste stream, and it seems to be ubiquitous in MSW in North America. And we see it, we've run into it at some of these sites we've been working at. It really makes getting some of our dual phase extraction wells functioning efficiently. It can make that very problematic.
Yeah, and
Bob.
as far as
Right.
you know, that ETLF black goo, you know, we work closely with Robert and his O&M folks to institute more frequent pump cleanings and pump
Yep.
servicing. And we also oftentimes send samples of the particular site-specific material that's plaguing and fouling up, you know, force mains and pumps and even valves and things like that within the collection system and the liquids management system to different companies and ask them to see if their, you know, bench scale chemists can come up with some sort of a formula of stuff that'll work well to, you know, break that down. And so we oftentimes are involved with the chemical cleaning companies in trying to, you know, identify what works, what of their products might be especially effective at removing that stuff.
One of the questions.
We do have we'll put in dosing pumps with those chemicals in our force mains for the leachate extraction, but unfortunately in the wells themselves, those pumps are going to be fouling, and it's just a matter of monitoring them frequently and changing and cleaning them frequently. So it's very labor intensive, keeping those pumps up and running.
Somebody indicated that at their landfill, they're getting this waxy material where it's liquid around 100 feet, but it solidifies as it cools, and literally like a leachate candle wax.
Yeah.
It inhibits the operation of the pumps, it clogs the force mains, and once it becomes solid, they asked, do we have any experience with that, and if so, any good solutions?
I don't know that I've specifically have a good solution. I can only commiserate with that individual and say I too have seen almost a depth stratification in a single well where the material, you know, was clearly a semi-solid, had a, you know, low viscosity and looked like oil, almost like motor oil. And then further down, it changed to almost like grease, the type of grease that you put in a grease gun to grease wheel bearings or something. So we've seen that type of stratification where the properties of this semi-solid material changes with depth. I'm not sure that I have a solution to that, although we are engaged a lot with different pump manufacturers and pump reps to see if their pumps, you know, can handle that. And we thought a lot about different types of pumps, you know, maybe a grinder pump that's oftentimes used in something like the sanitary sewer applications. If we could find a pneumatic one of those, that might help the circumstance. I don't know, Robert, anything that you've had as a specific solution to that circumstance?
Well, what happens is when it cools down, we get a lot of scaling and scale. So in some of our sumps, we've used like sewage grinder pumps. So, and the pump is actually above grade. So we're sucking it and it's grinding the material to make that all that scale a lot finer so we can push it through and get it up out of there. And then once it's into the force main, we're dosing with the chemical to actually soften it up a little more so it doesn't scale and block our force mains.
Bob, I've heard. Great.
Go ahead. Well, I was just, one of the things we've observed is kind of consistent with some of these comments is that at ETLFs, where we get kind of a black liquid-like material that's not conventional black goo, but it appears to be just melted polyethylene. You know, we throw a lot of polyethylene into our waste stream. You throw out your sandwich bag, you're throwing out polyethylene. A lot of your grocery bags are polyethylene, and that melts around 200 C. And so we've got high temperatures. We'll actually get liquid polyethylene And that'll look like a black oily stuff. And then as it cools, it becomes viscous or greasy and almost will, and can become a solid if we cool it enough. The temperatures really change the mobility of a lot of these materials and leach it. And I imagine in some, like Robert was talking about, where things are cooler, that they tend to be more problematic because they'll tend to solidify more.
We'll probably come back to this subject before the end of this, our discussion today. I'm gonna hold off on this, Bob, on the wastewater issue. I know that's a quote unquote hot topic, no pun intended, relative to dealing with leachate. But I wanna kind of do a little shift over to the O&M side of things real quickly, if I could, and bring Robert into the discussion. And I know we had mentioned the issue of health and safety. I think Bob, I think you mentioned that issue, and I'd like you to talk a little bit about really the special precautions that you have to take when you're dealing with elevated temperature conditions and some of the gaseous emissions that are coming off that can be problematic.
Yeah, so what we start out, we don't really know what we're dealing with, so we will implement a program for the technicians, and we'll put passive air monitoring badges on them so we could identify what constituents are in the air and what's going to be affecting them, and so we can supply the proper PPE and the air monitoring that we're going to be doing. At one site, that second item there is we found higher concentrations of benzene. As Craig said, that's one of the constituents that you'll see when you have ETLF, and at this site they had higher concentrations that we were concerned of. So we got the proper gas meter that was had a PID and will read benzene. So when we know that our people are getting exposed to that. Also, in situations where we have high levels of CO and H2S, we'll be using supplied air and masks. But before we do that, we normally would like to put in engineering solutions to that by using blowers or fans to clean the atmosphere that they're working in, so it's safe, because that's the supplied air and the mask, it's difficult to work in, especially when it's hot outside and things like that. So that is I don't want to say last resort, but that is sort of the last resort that we would do if we couldn't find an engineering solution to get to have that atmosphere clean, such as fans or blowers for those guys to work in.
And I know one of the things also to take into account is really the physical configuration of the space that you're dealing with. If you're in a quarry landfill and you're below the rim of the quarry, you've got a physical setting that is different than if you're on the top of a landfill where you got a free flow of air going around.
That's right.
And I've seen cases where you have a 3-foot depression in a swale where gas will accumulate in that swale. And there have been people who have actually died in those kinds of situations. So the physical configuration, I think, is important. Would you agree?
Oh, yeah. I mean, it's exactly what you said. That gas can accumulate in a low spot, and especially if you're in a quarry, you're in the whole landfill is a low spot. So it's looking at it from a whole different perspective.
I asked Bob this question, so I'll kind of ask you the same one based on your field experience and perspective. Really, what are the challenges you face with liquids management and high temperatures at these landfills? What are the things that you're looking at and how you may be addressing them?
Well, what it is, it's manpower, right? It's because everything's going to be more labor intensive. Once you start trying to pull out those liquids, and as we were talking, those sumps get fouled, or the pumps get fouled quite quickly. So it's a whole management plan where you're tracking those pumps, you're seeing how often they're cycling, and you're then choosing which wells have or which pumps are failed. You're identifying those, and you're creating a program to change them out on a regular basis. So it's somebody's going out there getting that data, and then you have another crew that's actually doing all the changing. So, and also that's from the liquids management side. And then when you see the temperatures, like they were also talking about, here's a melted wellhead. So you're using materials that are going to not melt, and those could be like Bob was saying, that could be hot at the surface. The technicians need to be aware of that and wear the proper gloves and everything when they're coming in contact with those now going to be metal surfaces and metal valves and wellheads and things like that. Also, here's a good example. You'll see that the top picture is how gooey and now solid the solids that build up on those wells and have them make them fail. But we have a cactus style wellhead is what we call it. So we can keep vacuum on the well if we need to pull the pump, and everything's hard pipe. So as we start to pull the liquids, you'll see geysering still occurring, but it'll occur internally into the well, and then the liquid will go into your vacuum header. So that's also an issue there, because you can start gunking up your vacuum headers with scale. And then here's an example of an active geysering well. Really, to handle this, you just have to let it settle down and get that pressure out. But you will get equipment out there, will berm the area so the liquid doesn't go all over the place, and then test the atmosphere and make sure that that it's safe for the guys to go in there, and they'll most likely hard pipe it with a cactus style wellhead and put a pump in there, and so we can start extracting that liquid and extracting the gas as much as we can.
So in terms of dealing with these sites, what tools do you use to track subsurface?
Yep. So like Craig was saying, tracking and trending is the most important thing. So you need to be tracking and trending. At SCS, we have a set of tools that we call SCS e-tools, and we're able to filter all of our data and ask for to look at different data points. So we're seeing, we can look at the CO2 to methane ratio, we can look at temperatures, so we can filter all that data and we can trend it to start to see where our areas of that we need to be focusing in on. So that would be our data services would be for our wells. Here's another SCS RMC. This is to trend the liquids and silt and your well screen. So we're looking at the health of our wells over time. So that it shows what the screen you have available. And actually this is over time here. I don't know if you can, there's a right there. So you can pull that across and it'll show your liquids in the landfill and as it goes through time. I'm sorry.
No problem.
And then this would be tracking temperature. We also have, like Bob was saying, we can put in thermocouples in the landfill, and we also can put in thermocouples on the wellhead, so we can see real-time data of what's really happening, instead of just getting snapshots as you're monitoring the well on once or twice a month. You'll have real-time data to see what's actually going on. And
I know from a regulatory perspective, we're working on several sites where this kind of data is not only important from the regulatory perspective, but just citizens are also interested. We've had a couple of situations where this data is being published on a semi-periodic basis, so that they can see what's going on at this landfill that's located nearby. So it's kind of interesting.
Yeah, and here's a photo here of on the left is it's a real-time data of the wellhead temperature there. So you're seeing that, and then the photo on the right is a thermocouple that's in the landfill, and it's a borehole thermocouple. So they're reading just the temperature in the waste mass as it goes down. So that's helpful to see where we're really at and what the real temperatures are, what we're dealing with.
Yeah, and another case on the right, just in terms of temperature and material compatibility, those are some issues that we had to wrestle with.
Mhm.
Because when we did some initial monitoring of temperatures, it was at one temperature, and then as you got deeper, actually it got a little hotter, and so we had to change out some of the materials that we were using so that it would perform. And so my advice is think hot, plan for hot, and be conservative. And so that's probably the smartest thing I could say. One of the questions that was asked, this kind of gets back to the black goo question, is the person says we have force mains that have a mix of gas condensate with leachate, and they're wondering, does that contribute to the black goo?
It's a good
Probably-
question.
Probably hard to answer.
I don't know the answer to that one. Yeah.
I think,
good
I
question.
think, Craig, your point about the temperatures in terms of, you got a temperature where these various plastics melt. I think that to me is a really a good indication of what, in terms of the process that's happening, you're hitting that point and stuff is flowing. And it's
Yeah.
flowing into the wells. And there may be other reactions that are occurring, that he's indicating the gas condensate plus the liquids. There could be other chemical reactions that are creating problems. And we've seen things like what you call it almost like ball bearings, clear ball bearings that form, just all kinds of weird stuff that's happening in these various reactions that are out there.
It's just my speculation, but I suspect that the black goo, the polyacrylates, probably do not originate from the pure condensation process. In other words, you take a saturated gas and you change the pressure or the temperature to result in liquid separation and the knocking out of just gas condensate. I suspect that is not the source of black goo. But if somebody says, well, heck, I just have a condensate sump, no dewatering liquids, my condensate sump is showing up with black goo, then what I suspect is happening is liquids from the well are making its way through the wellhead, right, Robert? Like that happens, and so while you think you're just getting pure gas condensate, you may be introducing leachate from downhole in the well because of those high pressures, that geyser type thing. But I know the question was really about, hey, we're commingling gas condensate and leachate in a single force main, finding black goo. I'm not sure that it's wrong to, or that the black goo is originating because of the commingling. I think it's more likely attributed to the leachate than the gas condensate, personally.
I agree.
Yeah, I think that's probably the case as well, because temperature's changing probably in the force main as well. And so things that are flowing nicely with the leachate may start coming out of solution and sticking on surfaces. You get some changes in chemistry when you bring in the condensate as well. And we do know polymer conformation is sensitive to chemistry as well. And that may cause some things to want to drop out, but usually your leachate volume is so much higher than your condensate volume. I think that's probably not a factor.
One management strategy I've seen employed at most elevated temperature landfills is because of the ability to accept your entire industrial wastewater stream. So, talking about your wastewater POTW that you ultimately discharge all your industrial wastewaters, you have different sources. You have your bottom liner leachate, you have your gas condensate, and now at ETLFs, you have your liquid dewatering, basically your leachate out of the gas system. It does help that if you can segregate the gas system liquids, which tend to have a different chemistry than the true bottom liner leachate, to some extent, if you can segregate the portions of your site that may not be afflicted by a hot zone or the reaction of an ETLF from those that are, then you might find greater success from just keeping some portion of your site liquids from to be able to keep going to your traditional discharge outlet.
I wanted to just break in here. We are at the top of the hour, And we had scheduled this for an hour. We're going to keep on going for a couple of minutes. If you would like to stay, we welcome you to stay. As Diane indicated, this webinar is being recorded, so it will be available ultimately. But I wanted to give those folks who have planned for that hour to be able to jump off. And for those that are, we really appreciate you joining us. But we're going to kind of keep on going here for a couple of more minutes. One of the questions I was asked was any thoughts about well gravel packs getting silted and closed up, blocked up, and how do we mitigate that?
I suspect it's happening. I've heard of different landfills, both ETLFs and some non-ETLFs, trying to do an unclogging of the gravel pack through pressure liquid injection. In other words, jetting the well at the same time of vacuuming the well. I've also heard of using the various chemical cleaning companies' products by jetting with that chemical cleaning product into the gas well. My experience, and I have very limited experience at sites where it was done, it demonstrated some benefit, but it never really restored your well back to pristine, newly installed conditions.
Well, there's a thought for landfill gas, pristine.
One of the things that I've looked at, Bob, is just you are going to get some clogging of the gravel pack around the well. You were drawing liquid into it, we're drawing gas. The stuff is decomposing, so we've got a lot of things suspended in solution. And so, I always look at, make sure that you over design the well. A large diameter gravel pack. The casing's not so important, but the gravel pack, big 3-foot diameter gravel pack, is the way to go. So it's got lots of opportunity for pores to conduct leachate and gas. And if someone get clogged, that's okay. Go ahead.
And that gets to be a challenge if you're doing a deep well, for sure.
Oh yeah.
Because then you really, the techniques that you have, or the technologies for doing that, sonic drilling, you're not going to have a 3-foot diameter, bore going down there. Liz Simmons indicated that they've had dedicated force main lines for their problem areas, and they confirms that works very well. So kind of another testament to the idea of segregation, Bob.
Oh, that's a good idea.
Yeah. I want to give it a chance for either Robert or Craig or Bob Dick, if you have any kind of closing thoughts that you'd like to pass. I'll start with Robert first.
Well, it's first and foremost, it's always safety out there, and know when this is happening that it's going to take a lot more manpower and a lot more hours with engineering and O&M and all those things, and like Bob was saying, that it's almost a war zone at times out there, just trying to keep on top of all the things that are popping off. So,
Mr. Dick.
Yeah, just number one, react in a manner so as to stay focused on pragmatic and practical execution of the solutions, the best management practices, and try to keep your site from becoming a science experiment or a scientific study by the regulatory agencies. Easier said than done, I know. And I guess, the ETLF response focus areas or duties are in these 7 categories of system design and construction, heat accumulation and removal, liquids extraction, odor mitigation abatement, leachate treatment, monitoring and sampling, because we do need that information, and then settlement accommodation. And if you can use those 7 categories to make a deliberate and intentional battle plan and have some strategic visioning for what might happen to you that you need to start addressing while you're in that triage moment of war zone crisis management, there are some things that you can do to achieve a better outcome and ultimately work your way through it. Craig?
Yeah, I'll just share a little bit on that, 'cause I hit on really key points there, Bob. Yeah, 15 years ago, these ETLFs really scared us. We didn't know what they were. Now we just need to, we know how to manage them. We actually probably can prevent ones in the future. But we need to think, it's not just standard practice because it's a very different animal. We always have to be thinking about, well, what does this data mean? What is when we're seeing these conditions at our gas well, when we're installing it, what does that mean? What does it mean mechanistically? What does it mean from a fluid transport point of view? Thinking about how things are working and then creating solutions around the things that we observe. And that goes right to what Bob Dick was saying. What are these kind of 5 or 6 key things that you got to manage? How are they going to function differently in an ETLF, and then just design things pragmatically around that? You got to kind of throw out the standard tools and think of a new set of tools often, but it's the same principles. It's just thinking about them in a new way. So I guess I would close with that. But we can address these at every site. When these come up, we can address them, we can resolve it and get it back under control.
ETLFs are significant challenges. They are sometimes require significant resources to address them, because sometimes they can take a life of their own, and that you're dealing with not only with the public, you're dealing with regulations, you're dealing with lawsuits, you're dealing with all kinds of things that can come out of these. And so it really does require a team of people from lots of different perspectives, whether it's Craig, from the perspective of your research and the stuff that you've done that really kind of gets at the heart of what is this stuff and what really is happening, to the engineering side, Bob, you talked about, in terms of putting the materials together to deal with the problem. We got to deal with real issues. And then Robert, from actually having to turn valves on wells and put things together that don't fall apart because of the temperatures. Very challenging conditions. And I want to thank the 3 of you for taking the time really to put together this webinar, and hopefully it's been helpful to those that you have participated. I want to thank those who have joined us today and hope you have found it interesting. There are other resources out there, Environmental Research Education Foundation. I'll put a plug in for them. They've got some great resources and research that is being done on these subjects. Join us next month. We're going to talk about black goo on a follow-up on this subject. So we're going to kind of do a deeper dive into black goo. I love that term. You got to patent it or copyright it, Craig. And there's other information on the SES website if you're interested in kind of digging into that. But again, Robert, Craig, and Bob, thanks so much. And again, thanks for all of those who joined us today.
Thank you.
Yeah, thank you. This has been great. Really appreciate the opportunity.
Okay, have a good day, everybody.